Hi folks, welcome to chapter 11. In this chapter, we are going to be looking at solutions. Now, in solutions, we are going to be describing the concentration of a solution. So what you see here is a cup of tea, and in the cup of tea, we usually add sugar into the tea. So when you add sugar into the tea, that forms what is called a solution. And we describe a solution as a homogeneous mixture of a solute and a solvent. So we are going to see what is a solute, what is a solvent, and how we can describe the concentration of the solution. So let's look at what a solute is. A solute is the substance that dissolves. So in this tea, we have sugar that has been dissolved in the tea. So the solute here is the sugar. The solvent is the major component of the solution, which is the tea here, the boiled tea, that is the solvent. So what is concentration? Concentration refers to the amount of solute that is present in a solution. So depending on the amount of solute that is present in a solution, we have different descriptions that we can give. So the first one is a dilute solution. And a dilute solution is a solution that contains small amount of solute. We also have a concentrated solution. A concentrated solution contains large amount of solute. And we have a saturated solution. And a saturated solution contains the maximum amount of dissolved solute. Alright, so we are going to see the ways that we can use to describe concentration. So we are going to look at basically three ways in which we can describe concentration. The first one will be the percent composition. The second one will be the fraction. And the third one that we are going to see later is going to be the molarity. So let's start with the first one, percent composition. So what is percent composition? We are going to look at two. We are going to look at percent by mass, and we are going to look at percent by volume. So when we talk of percent by mass, what do we mean? So mass percent is given by the formula, the mass of the solute divided by the mass of the solution times 100. So when you see mass of solution here, it is the mass is a total mass. So the mass of the solute divided by the total mass times 100. So that is the mass percent. We often times describe it as percent mass for mass. So we also have the volume percent. So when you talk of the volume percent, you mean the volume of a solute divided by the volume of solution, which is the total volume, times 100. So oftentimes we describe it as percent volume for volume. Now as an example here, when we talk of a 5% volume for volume bleach in water, that means we have 5 milliliters of bleach in 100 milliliters of the solution, which means that in that 100 milliliters, we have 5 milliliters of bleach and 95 milliliters of water. So when you see 5% volume for volume bleach in water, it means that there are 5 milliliters of bleach in 100 milliliters of the solution. So let's look at an example here. A cleaning solution contains 2% volume for volume ammonia in water. What volume of ammonia is needed to prepare 10 liters of this solution? So the first thing that we are going to do, we state the formula again, and this time using the 2%. So the 2% here is equal to the volume of the solute divided by the 10 liters of solution times 100%. So we have 2% volume for volume in water. So what volume of ammonia is needed to prepare 10 liters of this solution? Alright, so we are going to divide 2 here by 100, and then we multiply by the 10 to have the volume of the solute. So we have 2% here, and we are going to divide by 100, multiply by the 10 to have the volume of the solute. So if we divide 2 by 100, that gives us 0.02. And that is equal to the volume of solute divided by 10 liters of solution that we want to prepare. So to calculate the volume of solute here, we are going to multiply 0.02 by 10, and that gives us a volume of 0.2 liters, which is also equivalent to 200 milliliters. So you will need 200 milliliters of ammonia to prepare 10 liters of the solution. Now, let's look at the concentration by percent here, now in terms of volume. So the mass by volume percent is equal to the mass of the solute divided by the volume of the solution times 100%. So the volume here of the solution involves the solution and the mass of the solute that we have. So that is the total volume. So it is given by percent mass for volume. Now, it is always given in units of grams per milliliter. Solute, the mass is in grams and the volume is in milliliters. So when we talk of an example here, a saline solution, when we talk of a 0.9% sodium chloride mass for volume percent, that means that we have 0.9 grams of the sodium chloride in 100 milliliters of the solution. So the normal saline solution contains 0.9% mass for volume, which means that there are 0.9 grams of the salt in 100 milliliters of the solution. Now, seawater contains 3.5% salt in 100 milliliters. In the Middle East, there is the sea that is called the Dead Sea, and it has a very high concentration of salt in water. The concentration is 34% mass for volume, which means that if you take 100 milliliters of the solution, 34 milliliters of that solution will be the salt. Now let's look at an example here. Normal saline solution is 0.90% sodium chloride with a unit of gram per milliliter. How many grams of sodium chloride are needed to prepare 0.50 liters of normal saline solution? So we know that the normal saline solution contains 0.90% sodium chloride in 100 milliliters. Now, how many grams of the sodium chloride are needed to prepare a 0.50 liter of the normal saline solution? Now, the first thing is that we are going to see how many of these are found in a liter. So if we have 0.90 in 1 milliliter, how many of them are found in 1 liter? Okay, that means we have 0.90 grams in 100 milliliters. So how many of the grams will be found in 1 liter? That means we are going to have 9.0 grams in 1 liter. Now, with the 9.0 grams in 1 liter, we are going to use this to calculate the number of grams. Okay, so let's see. We are going to use this as a conversion factor to see the number of grams that will come out with. So the liters here are going to cancel with the liters and we are left with grams. That gives us 4.5 grams of sodium chloride. That is one way of doing it. Another way of doing it, that is a second method. We already know that in 1 liter we have 9.0 grams. So how many grams will be found in 0.5 liters? So we set up that equation and we still solve it. That will give us the same answer. So we know that in 1 liter we have 9.0 grams of sodium chloride. So how many of those grams will be found in 0.50 liters? So you can cross multiply here and you still come out with the same answer. That gives us 4.5 grams of sodium chloride. Now let's see how we can describe very dilute solutions. So when we are looking at water here, like the rivers or the streams, the concentrations are always so dilute that they are described in terms of ppm and ppb. ppm stands for parts per million and ppb stands for parts per billion. So here they will always contain very small amounts of substances that are dissolved in water. They could be heavy metals, they could be pesticides, they could be fertilizers. So they are always dilute and they have to be calculated in parts per billion and parts per million. So here in this case, we are going to look at the case of polychlorinated biphenyls. So polychlorinated biphenyls, there is a particular allowed amount by the United States Environmental Protection Agency that can be found in an amount of water, because high concentrations will lead to a toxicity that would destroy aquatic life. So according to the United States Environmental Protection Agency, the allowed amount, the maximum allowed concentration of the polychlorinated biphenyls is 5 × 10⁻⁴ milligrams per liter. Now, let's see how we can actually carry out the calculations involving parts per million and parts per billion. So for parts per million, it is the mass of the solute divided by the mass of the solution times 10⁶ parts per million. So this is where the per million comes in. And for the parts per billion, is the mass of the solute divided by the mass of the solution times 10⁹. So this is a billion, this is a million. Now, at 4 degrees Celsius, we know that the mass of 1 liter of water is equal to 1 kilogram for pure water, because water has a density of 1 gram per milliliter. So if you convert 1,000 grams, it will give you 1 kilogram, and 1,000 milliliters, it will give you 1 liter. So it will give you a mass of 1 liter, which is equivalent to 1 kilogram. Now, 1 part per million is equal to 1 milligram per liter, and 1 part per billion is equal to 1 microgram per liter. We are going to see some calculations involving the parts per million and parts per billion. So in a recent study, scientists found that samples from a European wastewater treatment plant contained about 45 micrograms of phthalates per liter of solution. What is this concentration in parts per million and in parts per billion? So we are assuming that the density of the solution is the same as pure water at 4 degrees Celsius. So why do we use this assumption? Because we know that 1 gram is equivalent to what? There is 1 gram per milliliter. Now, we are going to calculate the solute. We have been told that it contains 45 micrograms of phthalates per liter of solution. So the solute is 45 micrograms, and we know that 45 micrograms, we are going to convert it to grams. So we are going to have 45 times 10⁻⁶ grams. So that is the solute. Now we want to calculate the solvent. The solvent here is per liter. So the solvent is 1 liter, which is equal to 1,000 grams. So we know that is why we said we are assuming the density of the solution is the same as the pure water. So we said earlier that 1 liter is equivalent to 1 kilogram. So here, the 1 liter is equivalent to 1 kilogram, which is 1,000 grams. So we have to have the unit of grams. And we've said for the formula of calculating the parts per million, we've said is the mass of solute over mass of solvent times 10⁶. That is for parts per million. So that is what we are going to use here. So the mass of the solute is 45 times 10⁻⁶, and the mass of solvent is 1,000 grams times 10⁶. So that is going to give us a value of 0.045 parts per million. Now what about parts per billion? For parts per billion, instead of 10⁻⁶, we are going to have 10⁹. So we see here that for parts per billion, it's going to be 45 times 10 to the minus 6 divided by 1000 times 10 to the 9. That gives us a value of 45 parts per billion. Now let's have a summary of the concentration. We've talked about the mass per cell, which is the mass of solute divided by mass of solution times 100. We've talked of the volume percent, which is the volume of solute divided by volume of solution times 100. We've also talked of the mass per volume percent, which is the mass of solute divided by the volume of solution times 100. So we've looked at the parts per million, which is the mass of solute divided by mass of solution times 10 to the 6. We've talked of parts per billion, which is the mass of solute divided by mass of solution times 10 to the 9. Now let's look at the third way that we can describe concentration, and this is molarity. So molarity is given by the moles of solute divided by liter of solution. So the unit of the liter here of the solution here must be in liters or TM3. So when we look at this picture here, we see a sodium hydroxide solution that is 2 molar. So the molarity is 2 molar. Now we are going to see how we can calculate the molarity, and from the molarity we can calculate the volume as well as the number of moles. So the molarity is given by the moles of our volume, so we can calculate the number of moles by multiplying the volume times the molarity. Now let's look at this practice problem. An aqueous solution with a volume of 9.41 liters contains 412.3 grams of dissolved potassium chloride. What is the molarity of the solution? So we've been given the grams and we've been given the volume. Remember, for us to calculate the molarity is the moles over the volume in liters. So we are going to start by looking for the molar mass of potassium chloride. So after obtaining the molar mass of potassium chloride, we are going to obtain the moles using the given mass here. And from that, we will have the moles and we'll have the volume. From the moles divided by the volume, we are going to obtain the molarity. So let's start. The molar mass of potassium chloride is 74.55 grams per mole. And we've been given 412.3 grams, so we have to convert this to moles. As always, as we've said, we see here that grams will cancel with grams, and we are left with moles of potassium chloride. That gives us 5.531 moles of potassium chloride. Now we know the number of moles and we know the volume, so we can calculate the molarity, which is given by number of moles of our volume. So the molarity is moles of our volume, which is equal to 5.531 divided by 9.41 liters, and that gives us a value of 0.588 molar. So M stands for molar. Now, how many moles of hydrochloric acid are in a 250 milliliter sample of 6 molar hydrochloric acid? So we are looking for the moles here. We have been given the volume and we've been given the molarity. So one thing is that the volume must always be in liters. So we have the obligation to convert the 250 milliliters here first to liters. Then we are going to multiply the volume by the molarity to obtain the number of moles. So first, we know that molarity is moles of our volume, and we've been given the molarity and we've been given the volume, but the volume is in milliliters, so we are going to convert it to liters. So how do we do that? We know that 1 liter, there are 1000 milliliters. So if you do that conversion, you have 0.250 liters. Now we are going to multiply the volume by the molarity to have the moles. So we have 6.0 moles per liter. So molar is the same as moles per liter. Here we see that the liters will cancel with the liters and we are left with just moles, and that gives us 1.5 moles of hydrochloric acid. So let's see how we can prepare solutions of known molarity. If we dissolve 1 mole in 1 liter of water, does it give us 1 molar solution? It will not give us exactly 1 molar solution, because remember, molarity is given by moles of a liter of solvent, of a liter. So here we see that the moles here and the liter is actually going to be more than the liter. So it's not going to give us exactly 1 molar solution. Okay, so how can we prepare the solutions of known molarity? So for us to be able to prepare the solutions of known molarity, remember I just told you here that in the previous page that this will not give us exactly 1 molar, because we are using 1 liter and this moles, that means the volume is actually going to be more than 1 liter, and the concentration, or the molarity, we also call molarity the same as concentration, it will be different. So here, how can we prepare exactly the number of moles that we require? So the first thing is that we have to add the desired amount of the solid to a volumetric flask. After we calculate the mass that we need, we add it to a volumetric flask. That's the first thing. The second thing is that we are going to partially fill the flask and mix. So here, you mix such that all the solid dissolves. And after it has dissolved, the last step will be to fill it up to the mark, to the required mark right here. So you dilute to the correct volume. And here, you have prepared exactly a molar solution. Now, how can we prepare dilute solutions? So, for us to prepare solutions with specific dilution from concentrated solutions, there is an approach that we are going to use. Now, one thing that you need to remember is that the number of moles of solid do not change. Let's say you had 3 moles in 1 liter. Even if you use 1000 liters, the number of moles will still remain the same. So the number of moles do not change, but the concentration is going to change because the volume has changed. So the number of moles of the solid do not change, which means that the moles at the initial state are going to be the same like the moles at the final state. So what happens is that for a dilution, you just add an additional amount of water. So the actual intensity is going to reduce. So you see here, this solution is more concentrated than this solution. So the concentrated solution is more colored than the dilute solution. Now we are going to see examples of how we can prepare dilute solutions. So we know that the molarity for the initial times the volume is equal to molarity for the final times the volume. Since the number of moles do not change, we know that number of moles is equal to molarity times the volume. So the molarity for the initial times the volume of the initial is equal to the molarity of the final times the volume of the final. So let's look at an example here. You have 25.0 milliliters of air, 10.0 molar solution of potassium hydroxide. To this, you add enough water to make 500.0 milliliters of dilute solution. What is the molarity of the final solution? So here you have been given the initial volume, you've been given the initial concentration, and you've been given the final volume. So what you need is the final concentration. So we are going to use the formula, the molarity of the initial times the volume of the initial is equal to the molarity of the final times the volume of the final. So what have we been given? We've been given the molarity of the initial, we've been given the volume of the initial, but we don't know the molarity of the final, but we know the volume. So the molarity of the final is what we are looking for. So we make the molarity of the final here, the subject of this formula. So the molarity of the final is given by the molarity of the initial times the volume of the initial divided by the volume for the final. So we have everything right here. We just substitute into this equation, and that gives us 10.0 molar times 25.0 milliliters divided by 500 milliliters. So milliliters cancels with milliliters here, and we are left with molarity. So that gives us a value of 0.500 molar potassium hydroxide. Now let's look at a second example. Starting from a 12.0 molar concentrated hydrochloric acid solution, you need to prepare 180 milliliters of 1.0 molar aqueous hydrochloric acid. What volume of the concentrated hydrochloric acid do you need? Now, you have the concentration for the initial concentration. Now, you've been given the volume that you need to prepare and the concentration that you need to prepare. So how much of the initial do you need to use to come out with a 180 milliliter solution of 1 molar? So we are going to state our formulas. We know that the molarity of the initial times the volume of the initial is equal to molarity of the final times the volume of the final. Here we have everything except the volume of the initial. So we are going to make the volume of the initial the subject of the formula. So the volume of the initial is given by the molarity of the final times the volume of the final over the molarity of the initial. So we have everything here. We are just going to substitute into this equation. So we have 1.0 for the final, that is the final molarity, times the final volume divided by the initial molarity. So molarity will cancel and we are left with the volume here in milliliters. So that gives us a value of 15 milliliters of the concentrated hydrochloric acid. Now let's look at electrolyte solutions. In chapter 6, when we were looking at compounds, we looked at ionic compounds and molecular compounds, and under ionic compounds we looked at electrolytes, where we said that ionic compounds dissolve in water to produce electrolyte solutions, and so electrolyte solutions contain dissolved ions. Here in these two pictures, we see that when we introduce an ionic compound in water, the water molecules pull the ions away from the solid and into solution. That is exactly what the water molecules are doing. So what you will understand here is that the part of the water molecule pulling the negative ions is different from the part of the water molecule here pulling the positive ions. So in the solution, the positive ions are surrounded by the negative ends. So the positive ions are surrounded by the negative ends, the oxygen, and the negative ions are surrounded by the positive ends, the hydrogens. So that is how they dissolve in water. Now let's look at ionic equations. So a molecular equation shows the ions together as a compound, while an ionic equation shows the dissociated ions as separate species. Let's look at an example here. We'll see the molecular equation and the ionic equation. The first one that we are going to see is potassium bromide solid. The molecular equation is going to be potassium bromide in aqueous solution. So that is a molecular equation. Now, how is the ionic equation going to look like? The ionic equation is going to contain the potassium bromide dissociated into its potassium ions and its bromide ions. So that is what we see here. The ionic equation contains the potassium ion and the bromide ion. Now let's look at a second example. The second example here is going to be hydrogen bromide gas. Hydrogen bromide gas here. The molecular equation is going to be hydrobromic acid, and the ionic equation is going to be the hydrogen ion and the bromide ion. So this is the ionic equation, this is the molecular equation. Now let's continue to see the electrolyte solutions. Let's look at an example here of magnesium chloride. So this is 1 mole of magnesium chloride. when the magnesium chloride dissociates, what is it going to give us? So when magnesium chloride dissociates, it's going to give us a magnesium ion and 2 chloride ions, because they must be balanced. So magnesium 2 plus 2 chloride ions. So 1 mole of magnesium chloride is going to give us 1 mole of magnesium and 2 moles of the chloride. So it's just the same like you have a cheese sandwich, and in a cheese sandwich you have 1 slice of cheese and 2 slices of bread. That's the analogy here. So one cheese sandwich contains 1 piece of cheese and 2 pieces of bread. Now, what is the concentration of sodium ions and sulfate ions in a 3.5 molar solution of lithium sulfate? So how can we solve this problem? We first of all start with the formula of lithium sulfate and see how it dissociates into its ions. Then we are going to see the concentration of the ions. So lithium sulfate here dissociates to give us 2 ions for the lithium and 1 sulfate. Remember, it is from the balance, is from the compound. So we must have the same number of species on both sides. So 2 lithium, 1 sulfate, 1 sulfate. So we know that lithium sulfate is 3.5 molar. Because we have 2 of the lithiums, because in this 1 mole of lithium sulfate, we have 2 moles of lithium and 1 mole of sulfate. So in 3.5 moles, we are going to have 3.5 times 2 for lithium. That gives us 7. And we are going to have 3.5 times 1 for sulfate, because we have just 1. And that gives us 3.5 molar. Same thing. Now, write an ionic equation showing the ions formed when ammonium phosphate dissolves in water. What is the concentration of ammonium and phosphate ions in a 0.928 molar ammonium phosphate solution? So first of all, we are going to start with the formula of ammonium phosphate and how it dissolves in water. So if you don't know the correct formula, you are going to have it wrong. So the formula of ammonium phosphate is NH4 3, because the phosphate is 3 minus and the ammonium is plus 1. So when it dissociates in water, we are going to have 3 ammonium ions and 1 phosphate ion. So what is the concentration of the ammonium and the phosphate ions in a 0.928 molar ammonium phosphate? So we see here that 1 molar ammonium sulfate contains 3 molar ammonium ions and contains 1 molar phosphate ions. So 0.298 molar ammonium phosphate will contain that same amount times 3 for the ammonium ions. So that gives us 3 times 0.928, that is 2.78 molar. And for the phosphate, it is just 1, so it's going to be 1 times 0.928, and that gives us 0.928 molar. So that is all about the concentrations. Now let's look at another important property of water that we call the colligative properties. So the colligative properties, these are the properties of a solution, and they do not depend on the type of particles that are present in that solution, but on the number of the particles that are dissolved in that solution. And what are the colligative properties that we are going to be looking at here? We are going to be looking at 3 main properties, and those properties are going to be freezing point depression. So when there are particles in a solution, they lower the freezing point. So that is what we call freezing point depression. The second is the boiling point elevation. So when there are particles dissolved in a solution, they elevate. So they increase the boiling point. That is called the boiling point elevation. And the third property that we are going to see is osmotic pressure. Now let's start with the first one, the freezing point depression. Now, what happens as a practical example is that in winter, we always see the trucks here pouring salt on our roads. In a minute, I'm going to explain to you what that salt does. So looking at this graph here, we see here that the first in blue is sucrose, the second in orange is sodium chloride, and the third is calcium chloride. So we see here that at 0 degrees, this is the freezing point of water. So each of these substances is going to lower the freezing point of water, and each of them lower the freezing point of water depending on the number of ions, that each of them form. The one that has a higher number of ions is going to lower the freezing point more. So for calcium chloride is going to have 3 ions, sodium chloride is going to have 2. Here sucrose is a molecular compound and it does not dissociate, so it's just going to be 1 mole. Sodium chloride is going to be 2 moles, and calcium chloride is going to be 3 moles. So we see that for the sucrose, it gives us just 1 mole because it doesn't dissociate. Now for the sodium chloride, if we use 1 mole of sodium chloride, it's going to give us 1 mole of sodium plus 1 mole of chlorine, that is 2 moles. Now if we use 1 mole of calcium chloride, it's going to give us 1 mole of calcium and 2 moles of chloride, that is altogether 3 moles. So the effect of the calcium chloride will be 3 times the effect of the sucrose, and the effect of sodium chloride will be 2 times the effect of the sucrose. So that is why you see the freezing point will be lowered most by the one that contains the highest number of particles. So in winter, we see the salt trucks, they throw the salt on the ice. So what they do is that the salt actually reduces the freezing point of the water, and that clears the road, because for it to form ice again, it will need to get really colder. So that is how they work. When we pour the salt, it reduces the freezing point, thereby clearing the salt from the road. Now let's look at the boiling point elevation. Same thing, we know that for water, it has a boiling point of 100 degrees and a freezing point of 0 degrees. Now we see that we use ethylene glycol here in water, 40% ethylene glycol in water in our engines. So that actually does work in the engine. How does it work? Now water has a boiling point of 100 degrees, so we need some of those excess heat to be taken away. So we see that when we have ethylene glycol in water, it has a boiling point of 106 degrees, so that actually helps to take away some of the heat. And the ethylene glycol has a freezing point temperature of minus 45 degrees. So let's look at a question here. Which solution has the lower freezing point, a 3.0 molar solution of sodium carbonate or a 2.0 molar solution of aluminum chloride? So for us to be able to determine which of the solution has a lower freezing point, we have to see the number of particles that each of these is going to form, and we calculate the concentration of each. So let's start with the sodium carbonate. So we have 3.0 molar sodium carbonate. So when sodium carbonate dissociates, it forms the sodium and the carbonate. So we have 2 sodium ions and 1 carbonate ion, and the concentration is 3. So the concentration of the sodium ions is going to be 3 times 2, and the concentration of the carbonate is going to be 3 times 1. So that is going to give us 9 moles per liter. Now let's look at aluminum chloride. For aluminum chloride, the concentration is 2 molar. Okay, so for 2 molar aluminum chloride, it is going to break down to give us 1 aluminum plus 3 chloride ions. So for the 2 molar, it's going to give us 1 for the aluminum ion, 1 times 2, which is a 2, and for chloride, it's going to be 3 times 2, which is 6. So altogether, we are going to have 8 of the molarity. So which one will have the higher, which one will lower the freezing point most? The one that will lower the freezing point is the one that has the higher concentration of the ions, which is going to be the sodium carbonate here. Now let's look at the third one of the colligative properties, which is the osmotic pressure. Here, the osmotic pressure is really important in the biological systems. So in biological system, we are talking of the cell membranes, where the cell membranes separate the inner cell from the exterior, the interior from the exterior, and the membranes allow the passage of water from either of the sides depending on the concentration. So the membrane is described as being semi-permeable. And what does it mean to be semi-permeable? Semi-permeable means that water can pass through it, but molecules and ions cannot. So the membrane will only allow water molecules to pass through. All of these other ions, they cannot pass through, but only water molecules. You see here, the membrane is semi-permeable. Now, what is osmotic pressure? Water moves towards the more concentrated solution. So, the movement of water from a region of high concentration of water to a region of low concentration of water is what causes the osmotic pressure. So let's look at the osmotic pressure here. Let's say here we have just the water molecules, okay, and here we have ions. So what is going to happen is that for this membrane will allow the passage of water molecules, and water will move from this right side to the left side because the water is high here. So it moves from a region of high concentration to a region of low concentration. And when that happens, you see that the volume of the one here is actually going to increase while the volume here decreases. So this membrane here is semi-permeable. It allows only the passage of water. Now, what is the analogy of osmotic pressure? Let's say there are two towns, okay? We have two cities, town A and town B, and town A provide the same employment as town B. So they have the same population and they provide the same employment. So there will be no net movement of people because the number of people that are employed here because of the same population are equal to the number of people that are employed here. Even if people live here and work here, it will be the same. Now, in the second scenario, let's say town A launches a new factory and they're hiring people. Now, you will see that there will be a net movement of people from town B to town A because there is more employment in town A, and there will be less people that will be moving from A to B. So that is the analogy to the osmotic pressure. And in the third scenario here now, you see that as there is the net movement to A, the population of A is actually going to increase and the population of B will decrease because more people live from B to work in A. Now, for the osmotic pressure at a molecular level, we will see here that because this solution here contains ions, there is actually a low concentration of water. So there will be a net movement of water from this high concentration of water to the low concentration of water. So the net movement will be, you see, more of it will move to this side where we have a low concentration of the water. Now, let's look at the cells and osmotic pressure. So, like I said, osmotic pressure is very important in biological cells, where we are going to see, like in a hypotonic solution, we are going to see a hypertonic solution and an acetonic solution. So a hypotonic solution actually contains more of the solvent, so more of water. So if you put red blood cells into a hypotonic solution, it means water is going to move from the solution into the red blood cells. Because water is moving into the red blood cells are going to absorb, they are going to swell, and they can burst. So there is the net movement of water into the cells. Now let's look at a hypertonic solution. Hypertonic here means that the solution contains more dissolved solids. So because it contains more dissolved solids, it actually has a high concentration, which means that water is actually going to move from the cells into the solution. And when that happens, the red blood cells are going to shrivel, they are going to shrink. So you see the net movement of water from the red blood cells into the solution. Now, what is the ideal situation? The ideal situation is when we have an isotonic solution. For the isotonic solution, the rate at which the water is moving into the cells is the same rate at which the water is moving out of the cells. Now, that is applicable in medicine, where you have to be very careful, because if you have a hypertonic solution, the reaction is going to be contrary. As well, if you have a hypotonic solution, it is going to be contrary. So for intravenous substances, they actually use an isotonic solution. Now, let's look at an example of osmotic pressure. A 1.0 molar aqueous sodium chloride solution and a 1.0 molar aqueous calcium chloride solution are separated by a semi-permeable membrane. Which solution has a higher osmotic pressure? Will the water flow toward the sodium chloride solution or the calcium chloride solution? So, first we have 1 molar of each of them. So the one that is going to have a high osmotic pressure is the one that is going to contain more of the dissolved substances. So for the 1 molar sodium chloride, we are going to have a total of 2 moles, 1 mole sodium and 1 molar. We are going to have 2 molar, 1 molar sodium and 1 molar chloride. For the calcium chloride, we are going to have 3 molar, that is 1 molar calcium and 2 molar chloride. So you see we have more dissolved particles here in calcium chloride, and we will see that the net movement will be from the sodium to the calcium, because the concentration is higher here, there's a higher concentration. So water will move from a region of high concentration of water to a region of low concentration of water. So that is the calculation. We have 1 sodium, 1 chloride, that makes 2. And for the calcium chloride, we have 1 calcium and 2 chloride, that makes a total of 3. So the net movement would be from the 2 to the 3, because the higher total ion concentration will be higher in solids, and there will be the net movement towards that direction. So for the colligative properties, we've said that colligative properties do not depend on the type of particles, but on the amount, the number of the particles that are dissolved. We've seen the freezing point depression, we've seen the boiling point elevation, and we've seen the osmotic pressure. Now let's look at the reactions in solution. In chapter 6, we already saw the types of reactions, where we saw the precipitation reactions, we saw the acid-base, which are neutralization reactions, and we saw the metal displacement, where we talk of the single displacement and double displacement reactions. So for the precipitation reactions here, we will see that 2 solutions combine to form a solid product. 2 solutions that do not contain any solid. When you mix them, they produce a solid. So the solutions are not solids, they are liquids, but when you mix them, a precipitate is formed. So an example here, we are going to use silver nitrate and potassium chloride. This is the molecular equation. We are going to see the ionic equation, the total ionic and the net ionic. So here we are seeing that silver nitrate and potassium chloride is going to combine to form silver chloride and potassium nitrate. So the driving force here is the formation of the solid silver chloride. Okay, now the complete ionic equation, everything here will be ionic, except the solid that is formed. So the silver ion, the nitrate ion, the potassium ion, and the chloride ion, they'll combine to form the salt, which is the silver chloride, and the ions here, potassium and the nitrate ions. So for the net ionic equation, the net ionic equation cancels out all the ions that appear on both sides. So we have the silver ion here, which does not appear on this side, so it will not cancel out. We have the chloride ion here, which does not appear, so it will not cancel out. So the ions that we have on both sides, we have the nitrate, they will cancel out, and the potassium, they will cancel out, giving us the net ionic equation to be just silver plus chloride to give silver chloride. So that is our net ionic equation. Now, here is the precipitation reaction table. So you can actually look at this table to determine if a compound that is formed is going to dissolve or not. So here when you see this yellow, it shows that it is soluble, so no precipitate is formed. So when you see the blue, it means that it is insoluble and it forms a precipitate. For example, if we look at silver chloride, we see that silver chloride, so this is where they meet, silver and chlorine. This is where they meet, they form an insoluble compound. What about sodium chloride? So we look sodium here, this is chloride here, sodium chloride is here. It is forming a soluble compound, so there is no precipitate. So everything that you see here in the blue, the precipitate is formed. So that depends on the solubility of the product that is formed. Now, let's look at the acid-base neutralization reactions. So we saw that acids and bases combine to form a salt and water. Now we have hydrochloric acid reacting with magnesium hydroxide. This is going to form water plus magnesium chloride. So the driving force for this reaction is the formation of the liquid water. And this is a kind of a reaction where we call it's a double displacement reaction. Now, let's look at the metal displacement reactions. An ion of one metal reacts with the elemental form of another metal, and that is displacement. Let's look at an example here where we have this metal in solution reacting here. We saw that the solution there has been that displacement. Now, let's look at the molecular equation. So we have copper solid here dissolved in silver nitrate. Copper is going to displace silver, and we see that there is silver in solution. So here there is silver in solution. Now, the net ionic equation will be given by copper solid plus the 2 silver. Remember, we are going to dissociate here. So we are going to have copper ion plus the silver solid. So the silver has been displaced by copper to form the copper ion, and that is what you see here as a copper nitrate. So this is called a single displacement reaction. So the copper displaces silver to form copper nitrate. So we are looking at the reactions in solution summary and the classification and driving force. So the first that we are going to see is silver nitrate reacting with potassium chloride to give silver chloride and water and potassium nitrate. So what kind of a reaction is this? How do we classify this? This is a double displacement reaction, and the driving force is the formation of the solid, which is the precipitate. Now let's look at the acid-base neutralization. We are looking at hydrochloric acid reacting with magnesium hydroxide to give us water plus magnesium chloride. So what is the classification? This is still a double displacement reaction, and the driving force here is the formation of the water liquid. Now for the metal displacement, we've seen copper displacing silver in silver nitrate to form copper nitrate and silver metal. This is a single displacement reaction. So let's look at stoichiometry in solution. So we've seen molarity, we've seen the volume, and we've seen the moles. So as we saw in chapter 6, we can convert between molarity, volume, and the moles. So we are going to be looking at examples here. The first example, silver and chloride ions react as shown in the following ionic equation. Based on this, how many grams of silver chloride precipitate could be produced if 10.0 milliliters of solution containing 0.002 molar chloride ions reacts with excess silver? So here we've been given 10.0 milliliters of solution containing 0.023 molar chloride ions. So we are going to use the chloride ions to get back to silver chloride. So we are going to use the volume and the concentration to calculate the number of moles of the chloride ions. So after calculating the number of moles of the chloride ions, we will use this balanced equation to calculate the number of moles of silver chloride. And then, from the number of moles of silver chloride, we will use the molar mass to calculate the grams. So the first step, we are going to state that we have 10.0 milliliters of the solution which must be converted to liters. For that is for the chloride. And we have a concentration or a molarity of 0.0023 molar. Now, with the volume and the molarity, we can determine the number of moles for the chloride. So if we have the number of moles of the chloride here, we can be able to obtain the number of moles of the silver chloride using their mole ratios. And from the number of moles of silver chloride, we are going to obtain the grams. So the moles of chloride is the molarity times volume, and that gives us a value of 2.3 times 10 to the minus 5 moles of chloride. So we are going to use the balanced equation. The conversion factor here is that 1 mole of chloride gives 1 mole of silver chloride. So we are going to use the moles of chloride to convert to moles of silver chloride. So the conversion factor, 1 mole of chloride, 1 mole of silver chloride. So we are using this moles to convert to moles of silver chloride. So let's go. Now, the mass of silver chloride is 143.32 grams per mole. So this is what we are going to convert from moles to grams. So let's start with our moles of the chloride. So we have the moles of chloride. We are going to use the balanced equation to convert to moles of silver chloride. So 1 mole of chloride is giving us 1 mole of silver chloride. So that's our conversion factor. So we see that the moles of chloride here will cancel, and we're left with moles of silver chloride. From the moles of silver chloride, we are going to use the molar mass to convert to grams of silver chloride. So we are going to multiply that by that conversion factor. The moles of silver chloride cancel with moles, and we're left with grams. And that gives us 3.3 times 10 to the minus 3 grams. Now let's look at what we call gravimetric analysis. With gravimetric analysis, we are going to use the mass of a precipitate that is formed to determine the concentration of a reactant. Let's say, for example, we have a reaction that we are carrying out, and we use a particular volume of a reactant, and we are asked to calculate the concentration of the reactant. So with the product that we will form, which is a solid, we are going to do gravimetric analysis. Gravimetric analysis is weighing the grams of a solid that has been formed and converting the grams to moles, then using the balanced equation to determine the moles of the reactants. So we will be using lead 2 plus here reacting with iodide to give us lead 2 iodide. So what do we do in gravimetric analysis? So we are going to be determining the concentration of the iodide ions here in this solution. So how can we determine the concentration? So we are going to use the mass of the precipitate that is formed to determine the concentration of the reactant. So the first thing is that we need to measure out a known volume of the reactant. So here we have measured, let's say we've measured 50 milliliters of the unknown. The next step is that we are going to precipitate it with excess of the other reactant. Let's say we are determining our unknown here is the iodide. So we are going to react it with excess excess lead. So the lead here is in excess. So that is actually going to produce lead iodide. And we are going to filter the product that is formed and then dry it. After dry it, we will weigh the product. And then after weighing the product, we will determine the number of moles of the product. Because from the grams, we can divide by the molar mass of the lead iodide to know the moles of lead iodide. So from the moles of lead iodide, we are going to use the balanced equation to determine the moles of the iodine. Let's look at an example of a gravimetric analysis here. The concentration of sulfate ions in a solution may be measured using a precipitation reaction with barium chloride. The net ionic equation for this reaction is barium 2 plus reacting with sulfate 2 minus to form barium sulfate. Now, you need to measure the sulfate concentration in a large drum containing aqueous sodium sulfate. From the drum, you measure a 0.200 liter sample and then react this with excess barium sulfate. The reaction produces barium sulfate as a precipitate which you carefully filter and dry. The barium sulfate precipitate has a mass of 0.30 grams. What is the concentration in molarity of sulfate ions in the drum? So we are going to use this balanced equation to solve for the concentration of the sulfate ions. Now, we've been given the mass of the barium sulfate that was formed. So from the mass of the barium sulfate, we are going to determine the moles of barium sulfate. And from the moles of barium sulfate, we are going to determine the moles of the sulfate, as well as the moles of the barium if we were asked. So let's see how we can determine that. So the first thing is we are going to move from the grams of the barium sulfate that we have here to moles of barium sulfate using the molar mass. And from the moles of the barium sulfate, we are going to use the balance equation to determine the moles of the sulfate ions. And from the moles of the sulfate ions, we are going to use the molarity equation to determine the concentration. So we have 0.30 grams of barium sulfate. So we are going to use the molar mass of barium sulfate to determine the number of moles. So the molar mass of barium sulfate is 233.39 grams per mole. So the barium sulfate grams cancel and we are left with moles. So we are going to convert the moles of barium sulfate to moles of the sulfate. So how do we do that? By using the conversion factors in the balanced equation. 1 mole of barium sulfate gives 1 mole of the sulfate. So 1 mole of sulfate will be at the top and 1 mole of barium sulfate at the bottom. So the moles of barium sulfate cancels out and we are left with moles of the sulfate. So that gives us 1.32 times 10 to the minus 3 moles of the sulfate. But we've been asked to calculate the concentration. So now we have the number of moles and we have the volume. So we are going to multiply. So for the concentration, we know that the molarity is equal to the number of moles over volume. So we are actually going to divide these moles by this volume. So that gives us 1.32 times 10 to the minus 3 divided by 0.200 liters. And that gives us a concentration of 6.60 times 10 to the minus 3 molar. Now, looking at this map here, we can move from any direction to any direction. If we have grams of compound A and we have to move to moles, we are going to use the molar mass. If we have the grams of compound A and we have to move to moles of other elements, we are going to convert from grams to moles of A, then use the balanced equation to convert to moles of other compounds. If we have the grams of A and we have to move to atoms of A, we are going to convert from grams to moles using the molar mass, then we are going to use the Avogadro's number to convert to atoms. So if we have grams of compound A and we have to move to the volume or the pressure, we are going to first of all convert to moles, then we use the ideal gas equation that we saw for chapters 4, I think. So that is how we use this map. Now, in this case, we are given the number of moles of sodium hydrogen carbonate in this equation. So we have sodium bicarbonate reacting with hydrochloric acid to give us sodium chloride plus water plus carbon dioxide. Now we've been given the number of moles of sodium bicarbonate. How many moles of water are produced? So from this equation, we can do so many calculations. We've been given the moles of bicarbonate. So from the moles of bicarbonate, we have to move to the moles of water. We are going to use the balanced equation. So here, moles of bicarbonate, 1 bicarbonate to 1 water. So that's the conversion factor that we will use. So we start the solution. Here we are given the molarity and the volume of hydrochloric acid here. We have the molarity and the volume, and now we have to convert to grams of carbon dioxide. How do we do that? We are given the molarity and the volume. So we are going to use the conversion using the molarity and the volume to convert to moles of hydrochloric acid. And for moles of hydrochloric acid, we are now going to convert to moles of carbon dioxide using the balanced equation. And from the moles of carbon dioxide to grams of carbon dioxide, we are going to use the molar mass of carbon dioxide. So you can formulate any of the questions that you want here. So you can say, given 1 gram of sodium bicarbonate, how many grams of sodium chloride are you going to obtain? You just have to work that out. Now let's look at this example here. Now calcium metal reacts with aqueous hydrobromic acid to produce calcium bromide and hydrogen gas, as shown in the equation below. What volume of 2.50 molar aqueous hydrogen bromide is required to produce 200.0 liters of hydrogen gas at a temperature of 298 Kelvin and a pressure of 1.20 atmospheres? We have the balanced equation here, calcium plus hydrobromic acid to give calcium bromide and hydrogen gas. So we are asked to calculate what volume of 2.5 molar hydrobromic acid is required. So we are calculating the volume of hydrobromic acid. So how are we going to solve this problem? We've been given the volume of hydrogen, we've been given the temperature, and we've been given the pressure. So what do we need to do? We are going to calculate the number of moles of hydrogen. So if we know the number of moles of hydrogen here, we are going to calculate the mole ratio, and then we know the number of moles of hydrobromic acid, and we will be able to convert from the number of moles and the molarity to the volume. So let's see how we are going to solve that problem. So we are going to determine from the volume that we have here, we are going to use the ideal gas equation PV is equal to nRT to convert to moles of hydrogen. From the moles of hydrogen, we'll use the balanced equation to convert to moles of hydrobromic acid. And from the moles of hydrobromic acid and the molarity, we are going to calculate the volume. So let's start. PV is equal to nRT. This for hydrogen. So what is P? What is the pressure? So we are going to look for the number of moles. This implies N is equal to PV over RT, which is equal to, what is our pressure? Our pressure is 1.20 atmospheres times the volume. The volume is 200.0 liters divided by R is 0.08206 liters atmosphere Kelvin, and the temperature is 298 Kelvin. So we see here that we are looking for the number of moles, and our N here that you will give, that gives you the number of moles. Then we calculate that. So we have 298 times 0.08206, and we are going to multiply 1.2 times 200 divided by what we have at the bottom. So we have 9.8 moles. We have 9.81 moles of hydrogen. Now we are going to use the balanced equation to convert from moles of hydrogen to moles of hydrobromic acid. So we have 9.81 moles of hydrogen times, now in the balanced equation we see that 1 mole of hydrogen, we have 2 moles of hydrobromic acid. So we have 2 moles hydrobromic acid, we have 1 mole of hydrogen. So moles of hydrogen will cancel with moles of hydrogen, and we are left with moles of hydrobromic acid. That gives us 19.6 moles of hydrobromic acid. Now we have the number of moles of hydrobromic acid, we have the concentration. So remember, we say number of molarity is equal to moles over volume. Here we are calculating volume. This implies volume is equal to moles divided by the molarity, which is equal to 19.6 mole divided by 2.50. So that gives us 7.85 liters.